Hello everyone. Please allow me to start by welcoming you all and to ask my colleague Maya to also start the recording. My name is Gareth James Lloyd and I'm a senior advisor at the UNEP-DHI Partnership. And at the partnership, one of our focus areas is on water quality. I'm going to be your facilitator for this webinar today, and Maya Bertule, also of the UNEP-DHI Partnership, is going to be supporting me. If you'd like to learn more about UNEP-DHI Partnership and what we do, please check out our website. The main purpose of this webinar series is to raise awareness of the importance of water quality and to introduce participants to the main challenges, as well as ways in which these challenges can be addressed. The first webinar in this series, in that we looked at global goals and some of the lessons learned in water quality, and we had some cases both from Europe and developing countries. In the second webinar, we went into a little bit more detail on some of the key challenges in terms of the impact on water quality and the relation to human well-being, as well as looking at water scarcity and climate change. The third webinar looked at how to develop and apply governance frameworks, as well as some of the issues to be aware of when doing that work. For this fourth webinar, we're going to be looking at interventions to improve water quality. And thanks to Maya, all these webinars are going to be available online from our website. One second, I will just move on to the next slide. Could I ask my presenter colleagues just to make sure that their microphones are muted? I think I can hear someone. On the agenda today, we have a small group of very senior experts, and they're of course senior in terms of experience and not age. We have Jesper Dannisøe, who is going to be looking at water quality standards as well as technical solutions. We have Erichsen, who's going to be talking a little bit about types of water quality models and applications, basically what you can do with them. And rounding off the presentations, we have Claus Jørgensen, who will be giving us a presentation on bathing water and water in the landscape, and in particular tools linked to health and safety. We'll be rounding off the presentations as well by taking some questions at the end from you, the participants. So please feel free to use the box there on the right of your screen. You'll see there's a place where you can ask questions. Each presentation is going to be approximately 10 minutes with enough time, hopefully, for one or two of those questions immediately after each one. And I should probably round off by this slide by just saying that all of these webinars are going to be recorded and made publicly available on YouTube, and you'll be able to access them through the UNEP-DHI website. So without further ado, I will ask Maya to pass the microphone over to Jesper so he can tell us a little bit about those water quality standards and solutions. Thank you.
I think I'm on now.
Great.
Well, ladies and gentlemen, welcome to this webinar on water quality. I will give you an introduction to what I think about water standards and technical solution. My name is Jesper Dannisøe, and I have been working with water for many years, and I will share some of my experiences with you during this presentation. Now, water quality standards and the contents of what we use them for is what I'm going to talk about. So these are the contents of my presentation. What are the roles of the ambient water quality standards, discharge standards, and how to use them? Are there any technical solutions that we can use to improve water quality? And are there any alternatives to sort of the standard technical solutions. Now, I've been working in many years in different countries where I have met principles about discharge standards, and discharge standards is to some extent a very good thing, but one of the problems which I will highlight is that very often they don't seem to take into consideration that the discharge is going to hit a certain kind of water body. I have seen many places where you have certain types of water standards for discharge of different kind of industries and domestic sewage, and where you have some standards. But I think one of the problems about the standards is that they do not take into consideration what kind of discharge point they are discharging into. And what I've also experienced is that only very few countries actually have ambient water quality standards. I will give you an explanation about these two terms. Now, discharge standards, on the positive side, it's easy because if you want to establish yourself as an industry, you can simply look up on the internet or wherever you can get the information, and you can see that maybe the water quality standards for a discharge is 20 milligrams of BOD or 30 milligrams of total nitrogen. And sometimes there will be differences in the concentration level according to what kind of water body you are discharging to. Is it to a small stream? Is it to a river? Or is it to a river with water, drinking water purposes? So you can say that working with discharge standards is pretty simple, both for the authorities, because they can just look up, they can issue the permit, and it's very simple. And it's also easy afterwards to assess whether the compliance with the permit is on the right side. But the negative side is also there, because every water body is different, and water quality impacts will be different from discharging to a small river, discharging to a lake, discharging to a big river. And I think a very important factor that we sometimes forget in these discharge permits is that we forget what we call the load. And the load is the concentration of the substitute that we are discharging and the flow. And it's not very often considered. So in principle, you can discharge 20 milligrams of BOD per liter. And if you have 10 liters, it's going to be a relatively low load. If you have 10,000 liters, it's going to be a big amount that is going to be discharged into the water bodies. So that is one of the key issues, that we don't consider each water body before we actually give a discharge permit. The other one is also that very often you don't count in that there might be sources upstream who are also discharging with the same standards, and downstream also discharging with the same standards, and that means that you have pollution plus pollution plus pollution plus pollution, and in the end the system cannot simply cope with all that pollution. Now, compliance is also a big problem, that we can give out permits, but it's not always that we go out and check whether the permit is actually kept and whether there's a compliance with all the different components that we gave as what you can discharge. And unfortunately, there are many examples of the moment you have a discharge permit, it's more or less just a wildcard that you can use of how you want to do it, because the compliance and the control of compliance is not done systematically. So it's easy to cheat, and it's easy to discharge a lot more than what you have in your permit. And the other problem is that the people sent out to look at such a discharge, they may not have the power to stop a pollution because it's not in compliance with the discharge permit. And unfortunately, sometimes money speaks louder than the law and the legislation, and that means that some people will actually pay themselves to have a non-compliance, and they can keep on discharging. It's not very good for the environment, certainly not. Now, if you look at what ambient water quality standards is about, this is about finding out how much can a given water body actually take in terms of discharge. A large river can, of course, take a certain amount of discharge in terms of BOD or nitrogen or phosphorus without any big changes in the river. But a small river may not be able to cope with even a small discharge of maybe 10 milligrams of BOD per liter, because it will simply change the conditions in the river. So the principle about using ambient water quality standards instead of discharge quality standards is that you can actually make a tailor-made version that helps the water body to survive. And of course, there is a balance between the ambient water quality and the discharge. And that also means that every time you make a new discharge permit, you will have to look into what are the other dischargers to the river, what are the downstream and the upstream dischargers, have they already used up all the natural capacity of the river, so there will not be room in principle for a new discharge, or at least the new discharge may have to work with very, very high treatment standards. So important is that you have this overview before you work with it. And of course, you may also end up in a situation where you would say that if you want to establish your factory with a discharge in this river, you will have to find a proper treatment that can lower the concentrations down to a certain level which is acceptable for the water body and where you will meet the ambient quality demands. For instance, if you want to keep a good natural condition in a river, the BOD in the river should probably not be much more than between 2 to 5, 6 milligrams per liter. And that means just a little bit of extra things will actually push the river towards a lower quality and will hamper the biology in the river. When we also have the ambient qualities to work with, it's also very important that we again work with the load. How big is the concentration and how much are we discharging, so that we fit the permit so it actually also fits with the capacity of the river. Treatment systems to do all this, which are sort of some of the interventions, is of course basically very simple. Most of them has been around for many, many years. Unfortunately, many places they have not been implemented on factories, on industries, and on urban and city areas. The very simple one is that you have the mechanical one, where you in principle are only working with physical methods to have things to fall to the bottom of a reaction tank, and you don't work very much with the biology. But if you go up the next step to biological treatment, where you first remove all the solids with the mechanical treatment, and then you use the biological chemistry, so to speak, the bacteria and other biological elements to break down all this pollution, then you can actually get quite a good treatment and a much better discharge quality. And then you have chemical one, where you may design a specific method for removing, for instance, if the problem is heavy metals, then you will have to use a special system for that. So what you see in intervention, sort of the classical one, is that you have a mix of all these different combinations. You might have a mechanical chemical treatment plant, you may have a mechanical biological, and you may have them all three together. Now, these are very technical, very big usually, very traditional, but there are also some simpler systems. How about this one, a reed bed system, where you use the natural conditions in a reed bed that you construct to remove, for instance, nitrogen, phosphorus, and BOD, and it's very good for instance, domestic and also for agricultural runoff. You may also establish seepage systems, where you actually seep the water down into the ground and have the biology in the ground taking care of what is going to be taken away. And then you can also make very simple, I call them local scrap systems, where you actually make a bioreactor by crushing water bottles and use that as a tickling filter, where you in no time will have a biology that will actually break down the organics and some of the nutrients. In principle, something that can be established in any village at village level using local material. What are the alternatives if you cannot find all these ones? Well, the alternatives to lower the impact from the discharges is of course that you understand all the processes either in the domestic area or in your industry, and that you have a possibility to substitute harmful chemicals and only use those which are simple. And you look at the whole system to see whether there anywhere that you could go in and remove some of the polluting substances, so you would have a better water quality. And move products to places where sewage treatment plants are already there. That might be the best solution. So I hope that this presentation gave you a sort of an introduction to the fact that don't always work with the discharge standards. Also think about the ambient conditions and the ambient qualities that you have to. So the final one, the conclusions. Use of discharge standards may lead to overload in the water body. Ambient water quality standards are very important for the ecological balance, and very important is it also that compliance is done so that permits are kept, and tailor-made treatment can be used to reduce the impact. Thank you very much for your attention. I hope that this one gave you some good ideas.
Many thanks for that overview, Jesper. If you could just hang on a second and not close your mic just yet. There are a couple of questions here. The first one we have is, how is it possible to define ambient water quality criteria? Would you like to use a few words to respond to that?
Sure. This might seem like a very big problem to find out, but the interesting thing is that you will usually have some unpolluted water bodies in your country. Go out, make research on these one, look at what is the background concentrations of BOD, of nitrogen, of phosphorus, and all the different variables that you would work with, and you could use those as the ambient standards. So or you can look at the literature, because there will be a lot of references to what are typical ambient standards that you can use.
Very good, thanks for that. Second one, what do we do if we have several discharges on a river?
Yeah, this is a problematic one, because what you need to do is to actually go in and investigate what are the different components from each of the discharges, how big is each discharge, what kind of water body are you working with, and what is the load, that was the concentration times the flow, do you have from each of them, to find out is there any capacity left over in the river, and if not, then in principle you should not give new discharge permits. Okay,
great. Many thanks for that. I think without further ado, I will pass over to Anders. And Anders, as I mentioned earlier, will be going into a little bit more detail, looking at some of those water quality models and how they can be applied. So over to you, Anders. That's great.
Can you see?
Yeah, looks perfect. Now? Great, please go ahead.
Thank you very much. And thank you very much for giving me the possibilities of talking a little about models and which type of models we have available. And it fits very nicely into the end questions of Jesper's presentations, because one way of looking at these ambient concentrations and also how to assess discharge upstream could be by using some kind of models. I'm Anders Erichsen, I'm a senior engineer, and I have been working with models for many years, and hopefully I can give you some ideas of what we can do and why we need to model. First of all, I just want to mention what is a model. And a model is a simplified, limited, and pragmatic representation of the reality. That's a very important message, which we might try to model very different systems, but it will always be an abstract of physical reproduction. It will be simplified compared to real nature. It will just cover some relevant or necessary information. It will be limited and pragmatic, meaning that it will be designed to address specific questions, and it can probably only be used in a small set of questions related to that, and not answer questions beyond the scope of the model. It is valid. It means that it leads to correct answers, but only within a certain limit where you can use or apply that specific model. Why do we need to models, or why do we need models? Well, different things for use of model is hypothesis testing. Do we have an idea of an environmental problem, or a specific parameter or load, pollution affecting the water quality in a river? For instance, we could test whether it is possible or not, or that can explain the things. It's an intelligent interpolation or extrapolation between measurement points, for instance. We can use models for budgeting, looking at the entire mass of a carbon or nutrient within a system. We can use it for quantification and qualification if we have a model for a specific lake or river. If we change things, for instance, nutrient load reduction, or we construct a dam or anything else, what will be the overall effects of that? And we can use it as a management tool, and that fits very well into the things that Jesper said, in the sense that you could take your load standards and you can feed them into a model, and you can see if it has or which impact it will have on the river. And here you can, with a model, accumulate discharges from upstream rivers and rivers within the neighborhood. So in that sense, models can be used for a lot of different things. And which kind of models do we then have for the use of water quality modeling? Well, I've been working with process modeling for many, many years. That's what we call a biogeochemical model. We have been, or I have been working with this for mechanistic modeling, ranging from 0D to 3D representations. 0D is basically a box model. You could have 1D models, which could be a river model, or it could be a profile model from a lake. And you can have 2D representation, either surface or a transect, and you can have 3D representation. But this is very, these kind of models called biogeochemical models. You can also go beyond the concentrations of a certain substance and go into an individual or agent-based model, where we actually try to model specific behavior of agents. That could be fish, for instance, moving in a stream or a lake, or it could be the spread and settling of larvae of any species within the system looking at. Statistical models, I will just show a little bit of those. And population models is basically models looking at fish stocks, for instance. I will not go much into details of those, but these are kind of an overview of which kind of models exist. There's probably other models, but this is basically a good overview. Then there is somebody always answering, should we use models or should we use measurements? Well, measurements are always important, also when you do models. But measurements alone, I will claim, does not make a sound foundation alone. If you look at the figure on the right, you can see the red dots. The red dots are standard bottle measurements from Danish waters. It's basically a measurement point of chlorophyll once a month. But if you look at the blue dots, that's basically a ferry taking measurements more frequently. Or you look at the green one, which is a buoy that we have deployed in these waters. And as you can see, there's a lot of things going on between the red dots. And it's very seldom we have very high frequent model data, measured data. But if we have a model, we can try to integrate, or we can try to interpolate between measurement points, both in time and maybe also in space if needed. So measurements are being integrated into models, and models can be used for predictions or scenarios. You can change, you can try to model the situation as it is today, and then you can change nutrient load reduction and see if that has an impact on the ambient water quality. So an integration between measurements and models actually makes a very robust tool when it comes to different kinds of scenarios and management. Okay, I will just very briefly touch upon statistical models, which is basically as a model where you try to describe the correlation between water quality parameter and a pressure. A pressure could be nutrient loadings. It is very dependent on measured data. You set up statistical, you have a measurement and you have some pressures, and then you see if you can find statistical correlation between those. So you need measurements. And you probably need long measurement time series to include year-to-year variabilities and trends. And you also use measurements for validation. And on the figure on the right, you can see a result from a statistical model. It's observed total nitrogen on the x-axis and a modeled on the y-axis. And here, statistical model ranges from trend analysis in Excel to multivariable statistical analysis. One thing about those with statistical models is you have to be a little bit careful sometimes, I have an example here from the Danish marine waters. I hope you can look through that, but this is basically a relation that describes the depth limits of seagrass to the nitrogen concentration. There's nothing wrong with that correlation, but it's basically a spatial correlation, and it was used to define which nutrient levels you should reduce to get a specific depth limit. But that was a temporal estimation. You need the changes in nitrogen to get those effects on the depth limit, but the relation was a spatial relation, so you have to be very careful about what you use these statistical models for. Mechanistic models, or biogeochemical model, that's a mathematical description of causal relationships, and it ends up in a number of differential equations. It covers the biological knowledge and physical knowledge for a given area. It's a calculation on a high spatial and temporal scale and transferred into indicators in specific water bodies. Measurements are indirectly part of the development of equations, and measurements are used for validation. So these are the models that I will talk about from now on. Basically, we work with models in the sense that we have a hydrodynamic model that describes the physics, the current, and the water levels. We had an absorption dispersion model that transport matters. So if you have a nutrient concentration somewhere, where does it go? And we have an ecolab, and an ecolab is our process model where we kind of change the matter. We move BOD into ammonia, and ammonia into nitrate, and oxygen concentrations. So this is the way we work with biogeochemical modeling. Here's an example from river modeling. In rivers, you look mostly on ammonia, BOD, oxygen, maybe bacteria and viruses. There's an example of a schematic representation on the right. Primary production, not important in these kind of models, and very important to mention. Here I have an example from a river. It's an example we did for Göteborg water. We have a dam upstreams, we have some point sources down through the system, and in the city, basically they will have a drinking water intake, and here we want to make sure that the concentration of bacteria does not reach a certain level before they take in for drinking water treatment. This is the model. Don't look too much on that one. But here's the results. The green and red dots are measured E. coli concentrations, and the black line is an example of how we have modeled the concentration very close to that drinking water intake. And these kind of models can be used then to assess whether if we change a discharge upstreams, which effect will it have on the drinking water intake downstream. Other example of more complicated models is when you go into lakes or marine systems. Here you will have to look at things that have a primary production, plays an important role. I have an example here for some lakes in Sweden. Here we have three kind of algae. We have the red one, which is diatoms. We have the green one, which is flagellates, and we have the blue one, which is actually cyanobacteria. The figure on the right shows the total chlorophyll. And just to show you a transect throughout the river of the cyanobacteria, which is potentially toxic, you can see through this summer months that it develops pretty high concentrations, and it is very dynamic. The transect, you can see it goes from IP1 to IP2 on the figure on the left. Okay, concluding remarks. Modeling is a craft. It's all about applying the right model for the specific problem at hand. You can't do a BOD-DO model for a lake. It will not make sense. On the other hand, you shouldn't apply a full algae growth model for a river branch. It's all about applying the right model complexity. It should be just as simple that you can describe the thing at hand, but not too simple and not too complex. With models, you can assess a number of different problems. You can test different hypotheses, intelligent interpolation, budgeting tools, quantification, and management tools. And models are being used for interpolation between point measurements. Models are used for predictions, and integration between measurements and model make robust tools. So that was more or less my presentation.
Many thanks for that, Anders. I think getting in that modelling detail was very good. Earlier in the series, we've had a couple of comments from people who've joined us, and they wanted some more detail on the modelling side. And of course, it's natural that we say something based on DHI models. The question I have for you here is, which water quality models already exist within the MIC framework? I should probably just clarify for those listeners who aren't familiar with DHI that MIC is a range of modeling software products from DHI. Could you say a few words about that, Anders?
Sure. And of course, I have taken the offset in the DHI models, but I would say that the kind of modeling that I've been sending is available at a lot of different other softwares as well, and so but at the DHI, the MIC portfolio of models goes from very simple BOD, DO models to more advanced river basin models that includes different kinds of inorganic nutrients, including ammonia, inorganic phosphorus, and particulate phosphorus. We also have models on heavy metals. And then we have algae growth modeling, going from a little bit more simple algae growth modeling, including the entire nutrient cycling, into more complex modeling with more algae species and sediment pools of nutrients as well.
Great, many thanks for that. There's actually some more questions for both you and Jesper, so we're going to make some time for that at the end. I will now pass the microphone over to Claus Jørgensen. Thanks, Claus. Please go ahead whenever you're ready.
Thank you. I think I have unmuted my microphone now, and I will start.
Yeah, you're good. We can hear you.
Yeah?
Thanks.
And can you see me as well? Oh, here it is. Okay, so...
Yeah, we've got you.
Thanks. So my subject today is about bathing water and also water in the landscape. And I will focus a little bit on tools that we have and also links to health and safety. I am Claus Jørgensen, and I'm a microbiologist. I have been with DHI for more than 20 years, and my main interest is hygiene and assessment of health risk associated with human contact, so contaminated water. So the content of my talk will be a little bit about, in the beginning, about the WHO recommendations in relation to bathing water, and very briefly show a little bit from the European and the US legislation as well. Then after that, I will give you some examples on benefits, problems, and risks related to water quality in this context. Something about urban bathing water, and I have Copenhagen as a case. I'll give you some examples from Rio de Janeiro related to the Olympic Games, and then also to show you a bit about problems in developing countries, an example from Ghana as well. The WHO have issued some guidelines for safe recreational water, and the guidelines are based on they have a risk-based approach, and very shortly, this is about determining what hazards and risk that are present in a specific bathing location. And with that knowledge, we can implement measures to reduce the risks or keep people from swimming in the water. So the most obvious and prominent risk or the hazards are fecal contamination, which originates from sewage. Could be combined sewer overflows, or it could be wastewater discharge from treatment plants, but also riverine discharge can be a big problem. And what is not always thought of, the bathers, they contaminate the water themselves. So you can actually have infection transmitted from one bather to another. The WHO guidelines, they have a way of classifying beaches based on sanitary inspection and water quality. And the sanitary inspection is an assessment of the degree of influence of fecal material, or the evidence for this influence. Whereas the water quality is measured water quality. And if you take those two parameters, you can categorize beaches from very good to very poor in a very simple way. So the water quality is based on measurement of fecal indicators. So over the year, or over several years, you do measurements several times a year, and it can be enterococci for coastal and marine waters, or E. coli for fresh waters. And the WHO guideline has 4 categories. So if you have enterococci below 40 per 100 milliliters, or that is the 95th percentile of all the measurements that you have been doing, below 40, then the water is safe. We are below any reasonable risk. But if you go up higher, above 40, then there is a considerable risk of getting gastrointestinal illness or getting respiratory illnesses. And if you go even further up, then the risk is pretty high, and people don't usually recognize the high risk when you go swimming. So based on the water quality categories and categories related to the sanitary inspection, you can have you can classify your bathing water locations between very good and very poor, and from that classification you can take actions to either improve the water quality based on your knowledge from the sanitary inspection, or you can close down the beach. The European Union has similar water quality parameters. Here it is enterococci as well, and the US have recommendations. The US EPA have recommendations for the states, and they also operate with illness rates from 2 to 3 or 4%. So it is obviously that there is a risk, even though the water quality is pretty good. But the effect of wastewater is to be taken into account. So I will show you some benefits from urban water, bathing water, and I have a case here from Copenhagen, where we 20 years ago made a master plan for reducing the combined sewer overflows to the harbour with the aim of establishing bathing water locations in the harbour. And already in 1998, some very big retention tanks were established to reduce the overflows, and several others followed. In 2002, the first swimming facility in the inner harbour of Copenhagen was established, and along with that, we have used the DHI model to forecast the bathing water quality. For the time being, there are now 5 swimming facilities in the harbour of Copenhagen. For those of you who are not familiar with Denmark, I will just show you here. Denmark is in the middle of Europe, and if we zoom in on Denmark, you can see Copenhagen, the Copenhagen area to the right, very close to Sweden. And if you go even further, zoom further in, this is the part of Copenhagen where the harbour is. And this is a nice overview on a sunny day where people want to go bathing in the harbour, and you can see the harbour is very close, related to the city. and an overview here of the inner part of the harbor. And this is what it looks like. People are enjoying the water, and you can see very closely the city is very nearby, and it has had an very good effect, and people enjoy it a lot. We have introduced a bathing water forecast because even though we have built these retention tanks, once in a while there will be a combined sewer overflow. But we measure that overflow, and based on that we can model the water quality, and we can even have a forecast the next couple of days, and it is available on the World Wide Web. I will try to show you. I hope it works. You can see here it is loading on. Yes, here it is. I will zoom in a bit. Here is, you can see Copenhagen and the harbor, and here are different bathing locations, whereas these are the ones inside the harbor. And we can go for this one, for instance, and we can look. We can see, oh, that one is closed. We can take this one. We can see here at Lost Park and the water quality the coming days seems to be good. No precipitation. It's pretty cold. The water is also pretty cold, so I think not too many people will go bathing for the time being. Here it is. Oh, sorry. What happened? So the benefits that we have seen with the harbor baths are obvious. It has a very high recreational value. That was in July 2014, 90,000 bathers on one of the bathing facilities. It has increased the value of the real estate near the bathing locations. It's hard to decide precisely how much, but it is at least more than 10% and maybe up to 100%. And it's profiling the city very, very much. In 2010, the New York Times said that Copenhagen is one of the best places to go because you can go swimming in the harbor. And they see also that the way we do it is considered best practice. And even now, it's becoming more and more trendy to have bathing waters in the cities, and Copenhagen is one of the examples that are taken up in the literature. If you have poor water quality, on the other hand, like they have in Rio de Janeiro, and they are going to host the Olympic Games in 2017. If you search and make a Google search, you have 2 million people, 2 million hits concerning problems with the water quality.
Sorry for interrupting, Claus. 2 minutes, please.
Okay, I will finish in 2 minutes. The Associated Press, they made an investigation, and that gave very poor publicity for Rio de Janeiro and the Olympic Games. I will give you some information in developing countries as well. In Ghana, they have poor sanitation, which means that the urban water system is a health risk. Septic tanks are discharging wastewater into the roadside stormwater drains, and they want to invest to improve, but where do we get the best improvements? And that should be guided by health risk assessments. So what they did measured water quality, decided on exposure, decided doses that you get when you are exposed to the waters, and based on that you can calculate the burden of disease. And what they found was that actually 88% of the disease burden related to water came from ambient waters, and mostly these open drains. That was more than 60% of the disease burden, but also recreational water was carrying a big responsibility in this regard. So to conclude, fecal contamination of bathing waters poses serious risk of infection and illness. It should be managed with a rich risk management approach, including both sanitary inspection and water quality measurements. High quality urban bathing waters have a very high recreational value, whereas low water quality pose health risk and give negative publicity. And in developing countries, poor sanitation may create very unhealthy environmental water bodies and accounting for a large part of this disease burden. Yeah, thank you.
Many thanks, Claus.
That's it.
Please hang around a bit. I have a question for you here relating to your the study you presented on Ghana. What are the uncertainties related to this kind of study? Can you say a few words about that, please?
Yes, there are big uncertainties because the measurements being done are uncertain, and it's not all the pathogens that are taken into account. Exposure assessments are uncertain and so forth. So this kind of studies should be taken with big caution and be taken as a guideline of more than exact numbers. So, but they can be used to focus on where is the problem biggest.
Thank you. And a second question, other than fecal contamination, what other risks need to be taken into account with bathing water?
Yeah, there are other obvious risks such as drowning and sunburn, things like that, which is also related to recreational activities at beaches, and they should not be neglected. So if you have a strong currents, things like that, that should be taken into account when you assess the beaches.
Thank you. I'm going to use the opportunity to jump to the other presenters and pick up on a couple of questions we have outstanding there. I'll ask Jesper, please could you open your microphone?
Yes.
The question I have for you is it possible to limit the number of permits in a river?
Well, it certainly depends very much on the local legislation, but you could say that if a company or a discharger is not living up to his permits, then you should have the power to shut down, or at least to make sure that they are actually living up to their discharge permits. And if they don't do that, they should be shut down and removed. So but it depends a little bit on the local legislation, how much power is actually given to the environmental authorities.
In real life, how do people generally stop pollution from these kind of discharges? You mentioned, going around and shutting people down, but are there other approaches to doing this?
Yes, the other approach is called making treatment plants. Of course, that many of them do not have proper treatment plants. And what you see some places is that several companies may go together and create one common treatment plant. In some countries, they even have what they call industrial estates. That means that they have an area with a lot of industries, and they would usually have one or two common treatment plants. So the solution is to have them live up to their permits, and the other one is to create, for instance, common treatment plants that can take care of the discharge.
Thanks for that clarification, Jesper. Could I please ask Anders to open up his microphone? I have a couple of questions for you here.
Yep.
Great. Anders, are there any online modeling tools available for the listeners here to assess the problems of the kind that you covered in your presentation?
That I actually don't know. I haven't heard of anything, and I'm pretty sure there's no online. Whether there's any freeware, there will be some freeware, but I can't advise on those, unfortunately.
Okay, great.
Can I come in with a comment?
Yes, please do, Jesper.
If you search for the US, I think it's called the US Corps of Engineers, they are issuing, as far as I know, some models that you can download for free, but they are as they are, and there's not much support to them.
Just a quick clarifying question, Jesper. Are you aware if there's any support, or are they just take them as they find them, or don't you know?
I think there is a guideline for some of them, so you can get an idea of how they're working, but there's nobody to sort of to go to if you have any problems, no persons.
Okay. Yeah. Anas, another question for you, a bit more of a general one here. What does it take to build the water quality model?
To build the water quality, as in the equation of a biogeochemical model, depends definitely on the size of the model you want to construct. Model building is a number of steps. You need the hydrodynamics, you need the advection dispersion, but then you need the water quality model. And if it's that, if we talk about the water quality model, it's you actually have to kind of start up with a schematic structure of which state variables you want to assess, and then which processes you need to include, and then start building the differential equation. So it takes a number of steps, and you should definitely start simple and then add on complexity as you go along.
Thanks for that. Next question also for Anas. Please could you tell us the difference between agent-based and classic models?
Yeah. The classic models, or at least in the sense that I understand classic models, that's an Eulerian approach where you do concentrations of the state variables. So you have a concentration of nutrient, and that translates into another concentration of, for instance, an algae or something like that. The agent-based model is actually more or less independent on the hydrodynamic, or it can be independent on the hydrodynamics, and here you have an x, y, and a z coordinate applied to the agent, and you can make it, you set up a number of rules for that to act in the environment. So it could go for lower water depth or higher water depth, it could go for warmer or colder water, depending on the set of rules that you define. So that's basically on the Eulerian approach, or the classic, is a concentration, a passive drifter, and the process is related, whereas the agent-based modeling is on the individual agents that you set up rules for and then see how they behave in the environment.
Thank you. Last a question to Claus. Claus, can you please open your microphone? Are you with us?
Yes, I am.
Great. Question here. How is sanitary inspection typically carried out? Can you tell us?
Yes, the sanitary inspection is carried out on two levels. One is that you actually go to the site and inspect it and have a look on the conditions on the location, and you go search from one end to the other and see and record all the conditions. The other way is to go into historical information, such as water quality way back, but also maps. You can use maps to identify combined sewer overflows. You can identify rivers. You can identify other possible sources, and you have to take all that into account when you do your sanitary inspection. And then, based on measurements, water quality measurements taken at the present year, then you can make your matrix, which will give you an impression of the quality of the location, whether it's very good or very bad.
Thanks for that, Claus. I've got one eye on the clock here, and I'm afraid that's all the questions we have time for right now. But if you have any burning issues, please send an email to Maya, and she'll do her best to get back to you. Her email address is there on the screen. We're always looking to improve the quality of our work, so we'd be grateful if you could use a couple of minutes to fill in the feedback survey form that you'll be receiving from us shortly. We're also going to be sending you a link to the recording, and we're going to be making that available to you. The next webinar in this series on water quality will take place on Wednesday, November the 11th. The headline topic on this coming occasion is water quality management with a specific focus on tools and their application. So going into a little bit more detail there. As usual, we're going to have limited space, so please feel free to provisionally book your space by registering on our website via the link displayed there. Please allow me to conclude by thanking both the presenters, Maya, and of course you as the participants for once again taking the time to join us. We wish you all a very good morning, a good afternoon, and a good evening. Thank you.